So I changed the title of my talk a little bit, but with the latest release of Spectre, I really believe this to be true, and I think by the end of this talk, you will all agree with me. So this is actually my last slide. The rest of this talk will be in Emacs, which I think are the best kinds of talks. So Spectre is a library that solves a pretty straightforward problem, which is the ability to query and manipulate nested data structures. It's a problem that comes up constantly when programming Clojure. I've been programming Clojure almost 100% for 5 years, and this was always a problem that really frustrated me. Last year I decided I would do something about it, and I made this library Spectre. The cool thing about Spectre is not only is it a very, very elegant API for doing these manipulations, it's also extremely fast. And that's been a real focus point for Spectre. So I kind of want to demonstrate what I mean by these kinds of things being hard to do with just the facilities that Clojure provides on its own. So let me give you an example. So let's say the state of your program, or the state you're manipulating looks like something like this. So we have this variable called world, and it's a nested data structure with has 2 fields, people and bank. The bank contains funds, and then people is a list of accounts where each account has a money field and a name field associated with it. And notice that the people are indexed, let's just say they're indexed here in the order by which they join the bank. They're not actually indexed by their name. So if you want to get a hold of someone's particular account, you would need to do a scan and filter through that list. Now let's say you want to write a function which transfers money from a user to the bank. So let's see how you would write this manually using Clojure's base facilities. So here we have this function, user to bank, takes in a world and then a person's name and then the amount to transfer. And so the first thing we have to do is make sure, does that person have enough money to transfer that amount to the bank? If they don't, then we should throw an error. So what we do is we first navigate into the world data structure. So we look at the people. We filter for only users that have that name. And then the first one of those will be the matching user. We get the money. And then we check. If they don't have enough funds, we'll throw an exception. Otherwise, we now need to do this transformation on the data structure. And the transformation needs to decrement from the person's money and then add to the bank's funds. So first thing we'll do is we'll remove the money from the person's account. So we'll update the world data structure, and we'll update the people field, and then we give it the update function. And the update function takes in the list of users. So then we map over the list of users. For every user, if the name is equal to the name that we desire to take the money from, then we update the user by with the update function of subtracting the amount from them. And if it wasn't the user, we need to make sure to return the user, because we need to make sure to, for everything that's not getting updated, to actually reconstruct that original data structure in the outputted result. And I also want to emphasize that this mapv call, the reason we use a mapv instead of a map is because the type of the data structure here is a vector. If we used a map, it would change to a list. So it's really important when you're reconstructing your original data structure to maintain the types that were there before. Otherwise, operations you might try to do later might not work. And it's because some other operation changed some type that it wasn't supposed to change. OK, but after we do all that, next thing we can do is update the bank's funds. And update in is one of the very few functions Clojure has for doing nested operations. So you can see this is a lot easier. Take the bank's funds and add the amount to it. This code makes sense to everyone? Has everyone here written code like this before? I know. So to me, I hate this kind of code. First of all, I think it's really hard to read. It's really nested. The only logic you care about is adding to the bank's funds and subtracting from the user account's funds. And subtracting from the user account is in a deeply nested function within this overall function. And also, it's complex, because not only do you need to figure out how do I navigate into my data structure, you need to make sure to be very precise and reconstruct the data structure as it was, so that anything you're not changing remains as it was. So something really seems wrong here. But I just want to show what this function does. So I'll run this function on John Smith, and we'll take $25 from his account. And I have it set up here so that it first prints the world data structure before the transformation, and then prints the new world data structure after the transformation. So you can see John Smith has 25 less dollars and the bank has 25 more dollars. So now I'm going to show a function written using Spectre to do similar kinds of transformations. But this function I'm going to show you is actually way more general than the function you just saw. The function you just saw can only handle transferring from a single user to the bank. The function I'm going to show you here, it handles arbitrary many-to-many transfers of a fixed amount between accounts. So just to kind of elaborate on what that does, let's say you decide to transfer from 3 entities to 2 entities, and you're transferring $50. That's the amount that you give as input. So each of the 3 entities will end up giving $100 total, while each of the receiving entities will end up receiving $150 total. Okay? Because it's $50 is going between every pair of givers and receivers. So let's look at how this code works. And so first, so the arguments to the function, we take the world data structure, and then we take these 2 arguments, from path and to path. And these are paths within the data structure that identify the entities that we want to manipulate. And we'll see the details of this shortly. And then we take the amount we want to transfer between all entities. So first thing we do is we use Spectre's select function to select the amount of money that every giver has from the world. So we just say select from path world. So if we were selecting, let's say, John Smith and Charlie Johnson, this would return us a sequence of 100, 28, 2870. And then we do the exact same thing for the receivers. So we see how much money they have in their accounts. And then we compute the total amount every receiver will receive, which is just the amount multiplied by the number of givers, and then the total amount every giver will give, which is a similar computation. And then we check to make sure every giver has at least that amount. If they don't, we'll throw an exception. But if they do, then we'll take the world, and then we'll do 2 transformations on it. First, we will manipulate all the giver accounts and subtract the total give amount from them, and then we'll transform the receiver accounts and add the total received to them. Cool. So I do want to, so I think this code is really elegant. I think it's easy to follow. And every line in here matters. It has to do with the logic of what we're trying to do. And another cool thing about this function is this function is actually completely agnostic to the world data structure. Our user to bank function is specific to this particular world data structure, whereas this transfer function can handle any world data structure because the details of the structure we're manipulating are encapsulated in these paths that we pass in. And another cool thing about this function is that it can execute extremely fast. And we'll see that later. But of course, however this works depends on whatever magic that select, transform, and these paths are doing. So let's take a look at how all that stuff works. So we're just going to take a quick detour just to explore all this stuff. All right, cool. All right, so the first example I'll show is a pretty simple example of select. So we have a sequence of maps, and the maps all contain an A key, and you can see one of them contains a B key. And what we're going to do is get all the even values for A keys in all the maps. So the path that we'll give is, paths are just a sequence of navigation steps. And so the first step is to navigate to every element of the sequence. And then for every element of the sequence, we navigate to the A key. And then we only stay navigated there if it's even. So if we run this on this data structure, we get the results 2 and 4, just as we'd expect. So select is for doing queries where we want to extract values from some nested data structure. Transform lets us manipulate a nested data structure. So let's say we want to take the exact same structure and we want to decrement all the even values for A keys. So it looks almost exactly the same, except transform takes one additional argument, which is the update function to apply to every navigated value. And if we run this, we get, well, just as you'd expect. The first map had A go from 2 to 1, and then the last map had A go from 4 to 3, and the middle map where A was odd does not change at all. So I want to take you through how exactly this works, like how does Spectre handle data flow. So we'll see like what happens, what is the mental model you should use for the transformations happening at every step of navigation. So in this transform function, we start with this sequence as input, and then we do the all navigation. So the all navigation now creates basically a new navigation context for every element in the sequence. So you can see here we have 3 contexts, which is for each of the maps in the sequence. And then we run the A keyword to navigate into the maps. And so for every map, it navigates to the value for A. So we have 2, 1, and 4. Then even is a filter, so it only stays navigated where the number's even. So you can see now we just stop dealing with this number 1. And now we've actually reached the end of the navigation, so we apply the update function to all the values we've navigated to. So that's the decrement function. Now we have 1 and 3. And now we work our way back to reconstruct the original data structure, but only with these changes. So on the way back, the even filter just brings back any values that were filtered out before. So that was the number 1. And then the A keyword replaces the value in the map, in the original map, with the new values that we have here. So that's how we get these maps. And then all will take all of our navigation contexts and then put them back into a sequence, and all make sure to maintain the type of the sequence that we were looking at. So if it was a list before, it stays a list. If it was a vector, it stays a vector. Okay? And then that's the end of it, and that's how we get our results. And just to show you that all does maintain the type of the sequence, here's the exact same transformation, except with a list of maps instead of a vector of maps. And if I run that, you can see that you can see that the output is a list, not a vector, as you want. Cool. Is everyone following me okay? All right, cool, awesome. All right, so that's pretty simple stuff. Even a simple transformation like this is pretty tedious to write in Clojure. So let me show you a different kind of transformation you can do with Spectre. So this one right here, we have a big sequence, and we want to increment the last odd number in the sequence. So just think for a second about writing that in Clojure manually. It's not going to be fun. But in Spectre, it's very simple. We first use the navigation step filter odd, and what this does is it navigates us to a view of the sequence that only matches that filter. And the important thing is that we're still navigated at a sequence, not to the individual elements of the sequence. And then to that view of the sequence, which only contains the odd numbers, we navigate to the last value, and then we increment that value. But of course, when the update is applied, it's actually applied into the original data structure. So if I were to run this, you can see that we get a vector that's exactly the same, except that last 9 has now been incremented to a 10. OK, so let's take a look at, again, the data flow of how this works. So we start off with our input, which is this sequence of numbers. And then when we run filter odd, which navigates us to a view which only contains the odd numbers in that sequence. Then we navigate to the last value, which is going to be that 9, because it's the last value here. All right, we've now reached the end of our navigation, so we apply the update function. So 9 turns into 10. Now we go back. And what last does on the way back is it just sets the value of the last element of the sequence it was looking at. So that becomes 10. And then filter is really cool the way it works. Actually, when it does the original filter, it keeps track of the indexes that every element it captured in the filter was in the original sequence. So it knows that the 0th index of this view maps to the 0th index of the input. The first index of this view maps to the index number 2 in input, and so on and so on. So then when filter receives this sequence from last, it just sets the values in the original sequence by mapping the indexes. Okay? And that's the last operation, and that's how we get the output, which is what we wanted. Thank you, thank you, thank you. Here all weekend, folks. All right, so let's see some other transformations. So srange is a navigator that navigates us to a subsequence within a sequence. So here we navigate to the subsequence between indexes 3 and 9, and then we are going to apply Clojure's reverse function to that sequence. And that has the effect of just reversing all the numbers from indexes 3 to 9. So they're just reversed in the middle of the sequence. Of course, all navigators are composable. You can compose them arbitrarily. So let's compose srange with the stuff you've seen before. So let's take all the odd numbers between indexes 1 and 4 and add 10 to them. Okay, so that works fine. So srange, you can actually replace that sequence with whatever you want. It doesn't have to be a sequence of the same size. So here we will take the subsequence from indexes 2 to 4, and the update function will just return 5 negative 1s. If we run that, you can see that that subsequence has been replaced. It's a pretty common pattern, actually, that sometimes the update function doesn't actually care about the current value of that at that point. So Spectre has this function called setVal, which is just a very thin wraparound transform, which just lets you write those kinds of transformations slightly more concisely. So this code right here is the exact same thing as this code up here. Okay? If we run it, we get the same result. If you want to use srange to actually take out part of a sequence, you just say setVal on the subsequence, and then you give it the empty sequence, and that will nuke it from the sequence, as you can see. So this one right here, this is actually one of my favorite examples to demo. Here what we're going to do is we're going to take all of the even numbers between indexes 4 and 11 and reverse their positions. Okay? So the navigation is, let's navigate to that subsequence. Let's navigate to only the even numbers in that subsequence, and then reverse them. And then I'll run that. And you can see they've all been reversed. So just imagine, like this one especially, like imagine writing that in Clojure manually. Like, I mean, I wrote Spectre, and I can't even imagine doing this manually in Clojure. And this is like the power. This is the power of. I mean, Clojure's abstractions are actually very simple, but the important thing of how Clojure expresses those abstractions is that they're very, very composable, as you've seen. And this right here is the perfect example of the power of composable abstractions. Okay, so I have a few more examples. So this one right here, we have a sequence of sequences. You can see 2 of them are vectors and 1 of them is a list. And what we want to do is we want to append the values, the keywords A and B, to the end of every, to every subsequence. So the way we do this is we navigate to every subsequence, so that's using all, and then end navigates us to the empty subsequence at the end of the sequence. So we take that empty subsequence, which represents the end, and we replace it with a sequence AB. And that has the effect of doing an append. Right, so if I run that, you can see AB got appended to every subsequence. And also notice again, the types of the sequences we were dealing with are maintained. No. Yeah. Yeah. Talk to me afterwards. I can show you the implementation. All right, so something that happens pretty frequently is that when you get to the value that you want to manipulate in your data structure, you need information from elsewhere in the data structure to do the update. But since you've already navigated so far into it, you don't have access to the rest of the data structure yet. So as an example, the transformation we want to do here is we want to, for every map in the sequence, we want to add the value of the B key to the value of the A key, but only if the A key is even. So obviously, if we've navigated to the value of the A key, we have no access to the value of the B key. So Spectre solves this problem by letting you collect values as you move into the data structure. So the way we do it here is we navigate to every map, and then we collect the value for the B key. And this kind of gets put aside until we get to the update function. Then we navigate to the A key, we make sure it's even, and then we run the plus function. And Spectre will give as arguments to your update function first all of your collected values in the order in which they were collected, and then the value at the point we navigated to. So this has the effect of adding the value of the B key to the value of the A key, but only if the A key is even. So I'll run this. Right, and you can see that in the second map and the third map where A was even, B was added to it. Okay, so the last example I have here. So what we want to do here is we have a sequence of sequences of numbers. And we want to append the keyword CD to any subsequence that has at least 2 even numbers in it. So if you remember when we did this something similar before, to just append to every subsequence, the navigation was all end. But now we need to make sure that any sequence that we transform has at least 2 even numbers. So we need to add this filter between all and end. And we can express that filter in Spectre using this function called selected. And selected creates a filter at that point, and it will only stay navigated at that point if the path that you give it selects anything. So if it selects the empty sequence, we filter it out. If it selects anything other than the empty sequence, we keep it in. Right? And so again, we're just reusing all the same stuff, all Spectre paths. And so the way we know if something has at least 2 even numbers is we call filter even to get a sequence of all the even numbers. Then we call the view function in Spectre. So this navigates us to a view of that value where we apply the count function. So this will navigate us to the number of even elements in that sequence. And then we have a filter here. So we only keep that value if it's greater than or equal to 2. So at the end of this, if it has at least 2 even numbers, this will select 1 number. If it doesn't, then it'll select nothing. And you can see if we run this, only the sequences with 2 even numbers, at least 2 even numbers, had the append done to them. Cool. All right, so I want to show you real quickly a little bit how Spectre works. All right, so this is Spectre's core right here. It's this protocol. Everything you've seen, every single selector, all keywords, filter functions, filter, srange, all of these are implementations of this protocol. And let me show you, to actually explain how the protocol works, I'll show you a specific example. All right, so here's how keywords implement this protocol. So by now you've probably gotten the idea that when we're using keywords in the path, they're not used like normal functions. Obviously there's more logic associated with them, so they can do transformations and update values. And this is the implementation of how they work. So the way select works is it takes in the data structure that we've navigated to at this point, and then a next function which knows how to complete the select from any sub-values that we navigate to here. So to complete the select from a keyword, we just get the value of the keyword from the structure, and we call next function on it. And next function encapsulates the rest of the path to do the selection. Transform, the next function knows how to do the rest of the transform on whatever sub-values that we navigate to from this point. So to complete the transform from this point, we call next function on the value of the keyword. That will transform the sub-value, and then we associate that value back into the original structure, right, to reconstruct the structure as it should be. And that's it. I find this pretty intuitive, although I find some people have trouble like grasping what that next function does, but it's just easy to think of it as just it's the rest of the operation, and this is responsible for just applying it at this point. And I think this like perfectly captures the meaning of navigating via a keyword into a data structure. I'm going to show also the implementation of all very quick. Okay, so see all is the same protocol. In the select case, so all navigates to many values, to every value in the sequence. So what we want to do is we want to finish the selection from every value in the sequence. And remember, selection always returns a sequence of results. And so the total results will be the concatenation of all the results from each of our sub-values. So to do the select for all, we do a map cat of the next function over the structure. Okay? That's because the selection from every value returns a sequence that we need to concatenate. The transform case is different. Here we actually want to do a map, because next function knows how to transform every sub-value. So we do a map over the data structure to apply the transformation to every value. And the result we want is going to be a sequence, because all is looking at a sequence. And you can see there's a little bit more logic happening here. And all the rest of the logic is just to maintain the type of the data structure. Clojure makes this surprisingly difficult. And it turns out we actually need a special case for lists versus other types. But the overall logic here is it's just doing a map in the transform case. All right, so let's go back to the bank example. All right, so we have our transfer function, which we saw before. So it does fixed many-to-many transfers. So let's use that to do a variety of interesting transformations. So here we are going to do a transfer where every single person has to pay a $1 fee to the bank. So the way we do this is we navigate to the amount of money everyone has, and then the 2 is going to be to the bank's funds, and the amount we're going to transfer is 1. And you can see when I run this, everyone has $1 less, and the bank has $5 more. To do the opposite, where the bank gives $1 to every person, we just reverse the paths, we reverse the order of the paths. So now the bank is transferring to every single person $1. And if I run that, you can see that everyone has $1 more, and the bank has $5 less. So let's do a transformation where all the poor people have to pay $50 to the bank. This is kind of, I don't know if you guys have seen that Louis C.K. bit, but he has a whole bit about this. So the way we do this is that it's very similar. We navigate to everyone's account, except we only stay navigated when people have less than $3,000. Right? Otherwise, we transfer them to the bank. And you can see now that only the people with less than $3,000 now have $50 less, and I think the bank has $100 more. Okay, so here's a query. So let's get all the rich people, so people who have more than this amount of money. So we just navigate to all the people, and we only keep people where the amount of money they have is greater than or equal to that amount. And then we select that person's name. And you can see if we run that, we have Donald Trump. Okay, so what I have here is I have a function called user. So let's say we specifically want to deal with individual users. So this is a function that returns a path to a particular user using that scan and filtering strategy. So this is a function that takes in a user's name, and the path to that user's account, we navigate to people. Then for we will scan through every single account, and we'll only keep accounts where the name in the account, which is this, is equal to the name that we're looking for. Okay? So now we can use this to do other kinds of transfers. So to transfer between users, so we have a new function, transfer users, which takes in a from name and a to name, and then the amount. So we call transfer on the world, and then our path is we get the path to the user, and then we get their money, and then we get the path to the receiver, and we get their money, and then we transfer the amount. As you can see here, if I call this function to transfer $10 between Alice and John, that is exactly what happens. So you can see just how composable it is. We can construct a path here and then use it in another path here. Because a path defined as a sequence of navigation steps can itself be used as a navigation step in another path. Here we have a function called bank loyal bonus, where the bank gives $5,000 to the earliest 3 users in the list of accounts. So we transfer from the bank, and then we take the people, we take the first 3, the subsequence of the first 3 people, and then we grab their money, and we transfer $5,000. Right? And that transformation works perfectly. Just in the interest of time, I'm going to skip some of these. I will show this one, though. So this one has a selector, which I haven't showed yet. So here what we want to do is that we want to take our world data structure, and if for each person, if they have more than $100,000, we're going to add a new key to their map data structure with rich true. So the key is rich and the value is true. And if they don't, it'll be, all right, I'm going to change this to not so rich. I think I've definitely been in Silicon Valley way too long. So if the amount of money they have is more than $100,000, we set the rich key. Otherwise, we set the not so rich key. And the way this works is that we have this selector called if path, where it works kind of like if, where we have a condition. And if that condition matches, then we're going to use this path. Otherwise, we're going to use this path right here. And it works just like selected. If this selection returns anything, then it's considered true. If it returns nothing, then it's considered false. So you can see if we run this on the world. Let me compile. runs on the worlds. So some people have the rich key set, other people have the not so rich key set. And that's done using that conditional navigation. All right, cool. So I want to talk about performance. As I mentioned before, this is a major emphasis of the project, and Spectre has pretty amazing performance. So I'm going to show it by just actually running Spectre on a variety of little micro benchmarks. So the first one I'm going to show is dealing with this data structure here, data, which is just a nested map of keys A, B, C, and then all the way nested is the value 1. So let's see how fast it is. So the first one thing I want to show is just querying. So let's get that nested value from the map, and we're going to compare Spectre's performance against the performance of writing the code manually, as well as Clojure's built-in facilities, such as getIn. So I have this function here called benchmark, where it just times how long it takes to run this function this many iterations. So let me run this with getIn. Okay, so let me just. Okay, so getIn takes about 80 milliseconds to do this. So now let's run it using select, as I've been showing you, just select and then the path. And you'll see that it actually takes quite a long time. It takes 4.5 seconds, so that's absolutely terrible. And actually, it turns out that most of the work is actually just dealing with this path and interpreting it, and doing all the stuff Spectre needs to do to get it to work. So Spectre has this feature called Precompilation, where you can avoid doing all that work at runtime and just do the work beforehand and then just reuse that work. So the way you do that is you just call this comp paths function, which just takes in a path like normal, and it returns you this compiled path. So if we say select on the compiled path on the data, it takes 60 milliseconds, which is faster than getIn. But we can actually make it even faster, because if you know that you're receiving a compiled path, there's a function called compiled select, which strips out some of the overhead. And now it takes 50 milliseconds. So this is significantly faster than getIn. And I just want to compare this against like how fast can this possibly go by writing manual code. So let's just take the data and navigate to the value directly. And then here I wrap it in a vector just because select returns a sequence and I want to do a direct comparison. And you can see the best we can possibly do is a little under 40 milliseconds. So Spectre is pretty close to like completely inlined handwritten code. But the story gets even better when we talk about transforms. So let's take that data structure and let's update that nested value to increment it. So update in is the other facility Clojure has for doing nested transformations. Of course, only works on nested associative data structures. So let's see how fast update in takes to do the increment. So it takes about 10, 50 milliseconds. So now if we do transform without precompilation, takes a little over 4 seconds, so that's pretty bad. But if we do a transform with precompilation, it takes 180 milliseconds. So that's more than 5 times faster than update in. And again, we can make it better by doing compiled transform, because we know we have a compiled path. And now we're down to 170 milliseconds. Okay? And again, let's compare this against just doing the transform completely manually. So here I have a function which just does the transform via a bunch of nested update functions. And manual transform takes 150 milliseconds. So Spectre is super close to totally optimized handwritten code. All right. Cool. So that's been the story in Spectre for a long time, for many months. A couple weeks ago, Spectre's story got a lot better, because now Spectre can do precompilation in any scenario. And the scenario where it couldn't do precompilation before was where the path that you had depended on parameters in the function that you were in. So for example, if you had a function like this, where let's say we just want to turn that idea of reversing all numbers matching a predicate within a subsequence, like I showed before, if we just want to functionify that, it would look like this, where we have a sequence, we have a start position and an end position and a predicate, and then we transform that subsequence, but only elements matching that predicate, and we reverse them. So you look at this, it's like, okay, how do I precompile that path when I need these parameters to make the path in the first place? And Spectre couldn't do this before, because obviously you can't precompile something which you don't have yet, which isn't defined yet. The Spectre, in the 0.7.0 release a couple weeks ago, has a new feature where you can just precompile it without the parameters. And then later on, we'll sneak in the parameters, and they will be there. And let me just show you really what I mean by this. And so if we take like the simplest, so here's a key path. So this just navigates via any key. So it could be strings or numbers. It doesn't have to be keywords. And this takes in a parameter, which is the key we want to navigate by. And you can see we have the implementations of select and transform, which just use the key as if it's in the lexical closure. So when Spectre precompiles it without the parameter, it actually has these functions, and it's composing them, and the parameter is not there. But by the time this executes, Spectre sneaks in the parameter when it's provided later. This was a tricky thing to implement. But the way it actually works, if we go back to this example, where we wanted to make this function actually run fast, we compose the paths without the parameters. So sRange takes two parameters, which are not there, and then filter pred. So pred just acts as a filter, and it takes in as a parameter the function to filter by. So then we get this new path here called matching range, which matching range now requires 3 parameters, 2 for the sRange and then 1 for the pred. So before you actually use it, you just provide the parameters at the last second. So here we do compile transform, and then we give it the parameters at the last second. Okay? And then Spectre will map them to the correct selectors based on the order in which they were defined. So if I actually just do a quick benchmark of this, without precompilation, it takes 1.4 seconds. With precompilation, it takes about 600 milliseconds. So quite a bit faster with precompilation. The reason we don't get like the 10x improvements we were getting before is because these particular navigation operations are a lot more expensive than what we were benchmarking before, which is just navigating via keyword, which is super cheap. Filter and sRange, the work they have to do to reconstruct the original data structure is much greater. But still we get over twice the speed. Cool. So I have 3 minutes left. So I just want to show one more thing, which is just another example. So this isn't, I haven't open sourced this yet, although I do stuff like this all the time in my personal work. So I extended Spectre to deal with directed acyclic graphs, something I use very heavily in my own work. Honestly, making this library is not difficult at all. It's not a very long library. Just for me, it's kind of tied into my own stuff, so I haven't taken the time to extract it yet. But I'm able to do very cool transformations like this. So here, let's imagine we have a directed acyclic graph, which represents ancestry. So every node is a person, and it might contain fields like the person's name and their location and whatever other information we have about them. And then the edges in the graph are just parent-child relationships. So let's say we want to do a transform here, where we want to add a new field to every person, which is their royal name, which is just their name. It's going to look like their name of, and then the list of their parents' names. So we can do that transformation like this, where first we do a top sort. So we transform in topological order on the graph. And then for every node in the graph, we collect the names of our parents. So we navigate to every parent. And then for the node, which contains the fields, we get their names. And then we navigate to the node that we're looking at. And then we collect the current name. And then we're going to set the field for the royal name. So then our update function receives as input first the parent names, then this node's current name, and then the royal name, which doesn't exist yet, so we ignore it. And then our update function just does the concatenation. And that's it. After you run this, every node in the graph now has that new field added, which we wanted. So if you're looking to contribute to open source, I think this is a great project. That's not that hard, but very powerful and very cool. I have 1 minute for questions, so maybe we can do one question. I'll go right here.
Can you make any generalities about memory usage
It should be about the same. I mean, Spectre is not doing anything special with regards to memory.
Because the filter being kept around in the view and so on.
Right, but if you were to do that manually, you'd have to do the same thing. So maybe we'll take one more question. Let's go right there.
So I'm using Spectre in production, so thank you.
Oh.
One of the places I want to use that, whereas when you didn't know how you wanted to walk into something, or you didn't know the exact shape, something where I use zippers for now, and I wanted to reach for Spectre, but didn't want to go ahead. Have you thought about being able to walk around cursor?
I haven't run into that myself, so I mean, everything here is there because I needed it in my own work. And you can see, I mean, you can tell how heavily I use Spectre just based on how rich the library is. I haven't run into that. I don't know what it would look like. It'd probably be some sort of like, are you thinking like some sort of recursive selector?
Yeah, like instead of asking for a specific key, you start or something, just walk into a nested set of maps until it finds a map that looks like the thing it's looking for.
Right. Well, I mean, it does have a walk selector, which just does a walk, and you could use that to accomplish what you're talking about. Have you tried the walk selector? Yeah. It just uses Clojure.walk to do the walk. All right. Cool. Well, we're out of time, so thank you guys very much.